Hello everyone. Today we are going to discuss about the module 5 problems. Module 5, that is ideal gas and mixture. We are going to study about that module problems. Okay. Mm, the pressure and problem number 1. The pressure and temperature of gas is 7 megapascal and 150 degrees centigrade respectively. The critical pressure and critical temperature of the gas are 4.26 megapascal and 370 Kelvin respectively. Find the reduced pressure and temperature of the gas if R is equals to 0.19 kilojoule per kg and Z is equals to 0.54. Calculate the specific volume of a gas. What would be the specific volume of the gas if it is considered as the perfect gas? Considered as the perfect gas. Okay, this is the very simple problem. First, I'm going to tell which are the things are given in the problem. This is the existing pressure and temperature. The data is given. This is the data is given. But in most of the problem, the critical pressure and critical temperature they won't give. But in this problem, the critical pressure and temperature is given, as well as the Z values is also is given. R and Z value is also is given, that is compressibility factor value is also is given. So this is a very simple problem compared to the other problems. See, in this problem this critical pressure and critical temperature is given because in this problem which gas is not represented here is simply it is given as the gas, so this properties is given. Suppose in the other problems, instead of gas, if they given as the oxygen or a nitrogen or carbon dioxide, in such cases to collect these two properties you should go for the thermodynamics data handbook. But in this data, in this problem, this critical pressure, critical temperature, Z, all the values is given, so it is very simple problem. It is easy to find out the unknowns. See, we know that reduced pressure means reduced pressure means existing, sorry, reducing temperature means existing temperature divided by critical temperature. Reducing pressure means existing pressure divided by critical pressure. Okay, existing temperature is also is given, existing pressure is also is given, all the data is given. It's very simple, but the thing is the T and P is given in terms of a degree centigrade. You should convert into Kelvin. This is very very important. If you not convert it to Kelvin, you won't get the correct answer. So you convert all the things into a Kelvin. Now find out the TR and PC. Very simple. TR is equals to T is equals to existing temperature divided by critical temperature. Second here. So you get the correct value. Actually, this is the C, critical temperature TC. TC. This is C, 370 degree Kelvin. TR by TC is equals to 3670. So TR is equals to 1.14 value. Next, reduced pressure PR is equals to P by PC. P is given, PC is given, critical pressure is given. Find out PR. And Z value is given means you should use the critical compressibility chart equation, factor equation, that is PV is equals to ZRT. This is the equation 1. PV is equals to ZRT. Z value is already given. V is equals to ZRT by P. Substitute the values. Find out what is the specific volume. Next, in this problem, one more thing is asked. Calculate the specific volume of the gas, and also what would be the specific volume of the gas if it is considered as the perfect gas means ideal gas equation, that is what PV is equals to RT. PV is equals to ZRT, that is for compressibility factor. PV is equals to RT for the ideal gas equation. Now you take that perfect gas equation, ideal gas equation, PV is equals to RT. So V is equals to RT by P. R is given, temperature is existing temperature, P is existing pressure. Substitute the values, you'll get 0.011 meter cube per kg. This is a very simple problem because in this problem The critical pressure and critical temperature is given. It is given. Next, determine the specific volume of nitrogen gas. See, now this is, see this one exactly similar to the previous problem. Here also you have to find the specific volume, but not any unknown gas, but a known gas. It is mentioned as the nitrogen gas of existing pressure 10 megapascal and existing temperature 150 Kelvin, based on the ideal gas equation, that is PV is equals to RT, by compressibility fact chart, that is PV is equals to ZRT, and van der Waals equation. First, for this gas, for nitrogen gas, we should calculate, we should collect the all the properties. We should collect all the properties. Nitrogen. This is the given data, given data, and these things should be, we should be find out. Now go to the data handbook, thermodynamics data handbook, thermodynamics data handbook. This is the contents. See here, C6 critical properties, table C6 critical properties and characteristics, van der Waals constant. Okay, C8 van der Waals constant. These are the things are very now we are going to taking the values datas. Go to the C6 page number 58. Okay. See, our case is what? Which gas is given? Our case is the nitrogen. Nitrogen. Here you can see chemical formula, molecular weight, gas constant. Okay. These things is not required. These are not required for the current problem. This is not required at all. Okay, this values doesn't required. Once again, we required these things: critical temperature and critical pressure. Okay, for nitrogen chemical formula 28, gas constant 296.9 joule per kg Kelvin, and come to the critical temperature is minus 147, and the critical pressure is 33.94 bar. All these data should be transferred to the our problem. See here, all data I transferred here: molecular weight, R, TC, and the PC value I transferred to here. Once you collected all the data, now it is very easy to find out the unknown value V for all the three different equations. Come to the ideal gas equation. PV is equals to RT. PV is equals to RT. R is just taken from the data handbook. Just taken from the data handbook. Temperature is the 150 Kelvin, and P is the existing pressure. Substitute it here. Find out what is the specific volume. Next, van der Waals equation, van der Waals constant. That is the equation is P plus A by V square into V minus B is equals to RT. This equation should be by heart it. Otherwise, this equation is also available in the data handbook. See here, that equation is available. P plus A by V square is equals to V minus B is equals to RT. Okay. Now, see in this problem, now in this equation, we should find out what is the V value, but we don't know the value of A as well as we don't know the value of B. So this A and B values is available in the data handbook. See in the page number 59, page number 59, chart C8, you will get the van der Waals constant. And the van der Waals equation is also available here. There is no need to buy it at all. Okay. For nitrogen gas, you should collect all the data, but you should not take this one. This one should not be taken. This should be taken from the graph. Don't worry about this value. Only you take A and B. See, A is in terms of kilo, so it is multiplied by 10 power of 3. If you forget 10 power of 3, once again what the answer get is that is going to be wrong. I substitute the A and B value here. Now what I have to do? Same thing, you substitute all the values to the above equation. A to here, B to here, R is already taken from the data handbook, T is given temperature, existing temperature, P is the existing pressure. I substitute all the unknowns like this. Here V is the unknown. By using calculator, find out what is the this X value, that is specific volume. See here, one thing is the A value you obtained is in what? The kilomole is there. Kilomole is there. You should convert this kilomole into a kg. You have to convert it into kg. See here the answer is in meter cube per kg is there. So we also convert the specific volume. The specific volume should be in meter cube per kg. Here we obtained as the kg mole. To convert kg mole to the kilomole to the kilogram, to convert kilomole to the kilogram, you should divide it by molecular weight. Here molecular weight is 28. 0.039 divided by 28, you will get the this molecular weight is how much? 28. V divided by 28, you get this value. Next one is the compressibility chart. In the compressibility chart, you have to find out the Z value. See here, you have to find out the Z value. To find out Z value, first of all you have to find out what is TR and what is PR. So the reduced pressure is already, we know that the existing temperature divided by critical temperature. The existing temperature is 150, and this is the values taken from C6 table. Substitute here. Here also the existing pressure is 10 in 24 of C, and this is a critical pressure taken from the data handbook. Find out what is the TR and PR. Okay, once you find out TR and PR from the chart, okay, you have to find out Z is equals to 0.54. From the chart you should be find out this value. I will explain how to find out the Z value from the graph. See, for that one you should go for the chart number 7. Charts number 7. See, this is very simple one. In the x-axis, the PR term is there. In the y-axis, Z value is there. These values are what? These values are what? The TR values. TR values. TR values. Okay. Now, what is our TR and PR? The TR is 1.2. PR is 2.94. 2.94 means almost nearer to the 3, and TR is 1.2. 1.2. Now mark the points. Pressure is 2.94 is there, almost near to the 3. So here is the PR, and the TR is see here. PR is 2.94. I will mark here. And TR is 1.2. This is the line. This is the line. Okay. This is the line. This is 1.2. Now draw one straight line, and it should be cut the line. Somewhere this line will be get cutted here. This line is now touch the one. Now from this point, draw the line and fall on the Z value. Now, sorry, the somewhere it comes here. Plus or minus 0.2 will be various. Don't get confused about that much one. So now you'll get here. So this is 0.5, 0.2 and 0.4, 0.4, 0.6, 0.8 and 0.6. Here you're getting 0.56. But some, if you go from this point, it comes to 0.54. But some plus or minus 2, plus or minus 0.2 error will be there. That is not a big problem. Just this is the PR value, and select the TR value. If it is a 1.2 or a 1.5, and take the one vertical line and fall on that curve, and from that curve write the horizontal line that should be fall on the compressibility factor, that is y-axis. Find out what is the Z value. In this problem, Z is equals to 0.54. Now you take that value to the Z is equals to 0.54. We know that compressibility chart equation factor, that is Z is equals to PV by RT, or V is equals to ZRT by P. Just now all the values. Z is just calculated, R is taken from the data handbook, T is the existing temperature, P is the existing pressure. Substitute all the values, you'll get the specific volume is this much. Next problem. See, this problem is also exactly similar to the previous problem, but instead of finding out the volume, now we have to find out the pressure. Determine pressure exerted by carbon dioxide contained in a 1.5 meter cube capacity where it contains at 5 kg and 27 degrees centigrade, using ideal gas equation and van der Waals equation. So for the now, here volume is given in meter cube. You should convert into a what? Specific volume, or you can convert into a meter cube per kilomole. Why meter cube per kilomole? Means the van der Waals equation is containing a kilomole. So here you should convert it into a meter cube per kilomole. Specific volume is equals to volume of container into molecular weight divided by mass. 1.4 into 44 divided by 5. You'll get this is in the meter cube per kilomole. Suppose to convert meter cube to per kg, just you divided by this divided by 44. You will get meter cube per kg. That's all. Now, from thermodynamics data handbook, collect the data, but for carbon dioxide, where it is carbon dioxide, here carbon dioxide here is there. Carbon dioxide is given here. Take molecular weight, gas constant, and critical temperature and critical pressure. But in this problem, we are not using this one. Anyhow, you take the values. If you not take the values also no problem. We required only the molecular weight and gas constant because these things used in the ideal gas equation. Next, here the R is in what? R, the value R is in joule per kg Kelvin. Kg is there. Kg is there. To convert kilomole, just you multiply by 44 to convert into a kilomole. Okay. To convert all the units into 1 unit. To convert all the things into 1 unit. Whether you do in what kg or a kilomole is not a problem, but thing is all the units should be in the kilomole. Why I am converting in kilomole means in van der Waals constant a value is in kilomole, so here only I converted into kilomole. Now once you calculate all those things, you substitute the R value, temperature we know that one, just V is just we calculated, you substitute here, find out what is the pressure by ideal gas equation. Next is the van der Waals equation. Van der Waals P plus A by V square V minus P is equals to RT. RP is just simplify this equation. Next we have to find out the A and B value from the data handbook. Same table, that is the C8 in carbon dioxide, collect the A and B value. See, A is kilo, so multiply by 10 power of 3. Here you can see that is in the kg mole, means kilomole is there. That's why I converted specific volume into a meter cube per kilomole. Now you take A and B value. Once you take an A and B value, just you substitute, just you calculate, send all this value to here, the T value, R value, everything we know it, substitute all the values, find out the pressure. 1.87 into 10 to the power 5 Pascal. Here is 1.89. See, here is the one in ideal gas equation, 1.89 into 10 to the power 5 is there. By using van der Waals gas equation, 1.87 into 10 to the power 5 is there. Okay, after this, this is the one set of problem. This is the another set of the problem. I will explain in the next class.